Welcome to the Uptime Wind Energy Podcast. I'm your host, Alan Hall, president of WeatherGuard Lightning Tech. And today we're talking about a major issue facing the wind industry, leading edge erosion. Leading edge erosion is damage caused by the leading edges of wind turbine blades that hit raindrops, hail, dust, sand, all kinds of particles. It can lead to a decrease in efficiency, power output, and even premature failure of blades. Engineers and scientists are working on new materials to mitigate leading edge erosion, but they need to be thoroughly tested before being used on a wind turbine. That's where R&D test systems come in. R&D test systems builds the whirling arm rain erosion test equipment that many of you have seen on LinkedIn and YouTube. Now, this test equipment simulates raindrops impacting a wind turbine blade or aircraft up to 170 meters per second. That's about 600 kilometers per hour. That's really fast. To discuss this remarkable piece of equipment, we have Niels Peterson, Key Account Manager with R&D Test Systems. Niels, welcome to the program.
Thank you, Alan.
So leading edge erosion is this massive issue which affects pretty much every operator in the world. And the one complaint is it's just everywhere, and we don't know what to do about it, right? And that seems to be the big concern, is that they don't know where to go about it. And there seems to be all kinds of solutions in the marketplace at the moment, from coatings to tapes to these new shell devices. It's really hard to discern what is working at the moment.
Yeah, it really is. And we see a lot of coating manufacturers, of tape manufacturers, of polyurethane shell manufacturers tapping into this business because it is such a massive problem. And the business case is essentially really good. If you can solve this problem, then you have a really great business case. And that is the key thing, that this is just increasing the cost of energy, that we need to go and do repairs on the blades, offshore especially. And currently you need to do repairs every 8 years or something like that, depending on the location of the site.
Yeah, that is key, right? Is that as the tip speeds have increased, the blades get longer. There is more and more leading edge erosion, and numbers vary, but AEP losses typically are somewhere in 1% to 2%. I've seen AEP losses around 5% on some sites. It's amazing how much energy they're losing just because of erosion. And we had talked to a drone operator and asked them what was the number one thing they see in drone inspections. And the answer was, it's always leading edge erosion. Every blade has leading edge erosion of some level. And I thought that was astounding at the moment, because that was a couple of years ago when I first learned how deep that problem is. That always was interesting to me, just because it seems like that problem is solvable, but it is a very, very difficult problem to solve, as we're finding out.
Yeah, I had the exact same thought when I tapped into this. I would call it kind of niche technology and niche problem, but it is just such a difficult problem to solve. And you could imagine just these blades experience these massive amounts of rain droplets during a lifetime, just rotating all the time and hitting these droplets at 300-400 kilometers per hour. The wear is just really extensive.
It's amazing how fast the rain actually eats away at a surface. And having done and been involved in some rain erosion testing myself, until you see it up close, you realize this rain will eat through aluminum. It'll eat through metal. Forget about this fiberglass epoxy systems we're using on wind turbine blades. When it eats through metal, it's a little shocking at first. Like, oh my gosh, I don't know how we're going to solve this problem.
No, we're using aluminum specimens to calibrate our machine, and it is a soft alloy, but it's eating this aluminum in 8 hours or so. That is accelerated test, though. Yeah.
Yes. Oh, sure. So it tells us how important it is to actually evaluate materials. And I know for the longest time, the industry had, and aerospace too, because I've been in the aerospace industry a long time. The aerospace industry, and then subsequently the wind turbine industry, didn't really have a solution. There were a lot of independent test rigs, I'll call them. Like Boeing has a test facility. There's one from the U.S. Air Force that has a test facility, but they don't work the same. They're not consistent, and there never was really a standard to go use them. So you go to the different facilities, you get just two wildly different results, and you question, well, what's the validity of any of this? And I think that's, well, at the time was true, but a lot has changed since then, hasn't it? In terms of just standardizing what the rain erosion environment looks like.
Yeah, that was what we saw previously, that the OEMs basically had their own machine, and they were qualifying the materials they purchased from coating manufacturers or whoever who also had a machine to develop and verify their materials. But it was all different machines, and most of them were kind of homemade, um, and that's where we kind of found a niche offering in the market. So we made the first machine back in 2014, delivered it in Denmark, and since then we have then delivered 15 of the same machine, which performance can all be compared. And you can compare from OEM to OEM. You can compare from coating manufacturer to coating manufacturer, and even between test institutes and OEM if you're gonna third party validate your results. So that's really a game changer.
That's gigantic in the rain erosion world. And maybe just briefly describe what R&D Test Systems manufactures, right? It's a whirling arm system. So you want to just describe what a whirling arm rain erosion system looks like?
So basically, in contrary to most other rain erosion test setups, which basically vary from a high pressure washer to a small spray, we're going through a circular disc. This is the setup that resembles reality the most, and it's basically we're artificially making a rain field with a lot of needles, 600 needles, and then we have a small helicopter underneath this rain field, 3 blades mounted on them. In the leading edge of the blades have the test specimens, which can then easily be exchanged to new test specimens. And then we're rotating this basically underneath the rain field. And that gives us some really good results and some really high repeatability. And one of the interesting things about this is also, since we have the rotary movement, then we actually get the velocity profile of the rain erosion going from different velocities. So you get a lot of insight from this machine.
So as the blades spin, the water droplets fall, and the blade intercepts them, hits them. So at the surface level, what is happening as that water hits the surface of the test sample? What happens there?
Yeah, so basically, and that's also a fairly new discovery, that the rain droplet isn't in fact just wearing the surface down. It is actually microfracturing the surface of the blade and causing fatigue damage, and then in the end causing cracking, erosion problems, and that's what's happening there. And that's also why we see different phenomena of erosion going on at different speeds. And we see a tendency in these machines and in this area of testing that we want to actually reduce the speed to a more realistic speed and then increase the amount of rain density instead, because that results in more realistic conditions, because we're seeing different phenomena at higher speeds.
Okay, so the airplane analogy to the wind turbine blade may not be applicable because airplanes are moving typically faster than a wind turbine blade.
Yeah, so going a little bit, just very briefly, into the aerospace industry, it is a different problem. First of all, they're not experiencing the same amount of rain, only doing takeoff, landing typically. Then they experience it typically at higher speeds. But the biggest difference is really that it's fairly easy to maintain the leading edge of an airplane. They're in the hangar anyway, once a week, twice a week. Yeah, that's not the case for a wind turbine.
No, where it doesn't get as much oversight. So speed matters here. The way I've seen it described in recent literature is as the droplet hits the surface, it creates like a miniature microscopic shockwave, and it stresses the material and tries to break it apart and microcrack it, eventually microcrack it. And then once that happens, you just, all bets are off. It just starts to eat away. And that's, I agree with you. That's a more recent understanding of what is happening. And but that leads back to you have to have some sort of test results. You need to have a way to test it, because previously it seems like we were just learning from experience in the field. Some places would have horrible rain erosion. Other parts of the world have very little. And we didn't really understand. And different wind turbines, even though they're manufactured in the same method, the blades are pretty much identical. As they got longer, seem to have, in different airfoil shapes, you seem to have different kind of responses. It leads to, we need to be testing, and we need to be testing a lot of these coatings. And there, I think one of the pieces here I was reading about R&D Test Systems rain erosion package that you maybe first of all, let's just describe what the whole system looks like.
Yeah, so typically when we deliver a system like that, we have it in two 20-foot containers, opened up in the sides and then spliced together. Really creates the test chamber. And then besides that, we have another 20-foot container with auxiliary systems, electrical system, water treatment system, and operator facilities. And that's approximately half of the systems that we have delivered. This is in this format. And the other half is actually integrated into buildings. It's a little bit of, let's call it a nicer solution if you have the space, if you have the building available. Then you can mitigate noise problems a little bit. But it's really plug and play for us to deliver these machines. We ship these 3 containers. We have an assembly team coming to site, setting everything up. It's just sitting there on simple foundation points. And then we have it up and running in a matter of weeks or 1.5 months or so. We pre-assemble everything in our facilities in Denmark.
Remarkable. I've seen pictures of your systems. I think it was at LM Wind Power had purchased one of your systems. And I think you had a press release recently where DTU has purchased one.
Yeah, we just had a really good sale to DTU. We have had a lot of collaboration with DTU in terms of different funded projects, development projects, especially on the testing method itself and how to increase reliability and understand all the different parameters. And DTU have now been granted the funds to get a machine for themselves. And this is also basically showing that we are not at the end of this problem. We still need development, we still need research. And the machine that they have bought, it's going to be so cool. It's going to be delivered in start of 24, up and running. And what DTU has done is that they have asked, can we increase the amount of rain 3 times? Can we basically have 1,800 needles instead of 600 needles?
Wow.
So that's, I think, is going to be a game changer when suddenly we can threefold the amount of rain we can put on these specimens.
What's the rationale behind that to increase the number of raindrops?
It is that this is still a relatively expensive test to do. So you want to accelerate it as much as possible. And you want to then accelerate with the amount of rain instead of accelerating the velocity. Because accelerating the velocity gives you these unrealistic phenomenon in the erosion process. So by increasing the rain density, you're basically just dividing the number of testing time you need by 3. It should scale proportional.
Because it's already an accelerated test, right? The way that I've seen it operate now, this seems to run for hours, not days, to get some at least initial feedback.
Yeah, it is an accelerated test. You can run it at low velocities and basically replicate reality just with a lot of rain, of course. And we are seeing some customers actually running test campaigns at plus 1,000 hours to have these realistic data sets where they can see they have a lot of measuring points, see exactly how the erosion develops through time.
One of the things I hear from feedback on rain erosion is if you talk to an operator in, let's say, Brazil, or talking to an operator in South Africa versus an operator in Denmark or the United States, as they're seeing different kinds of or different levels of rain erosion, and you kind of scratch your head and go, well, rain is rain, isn't it?
Yeah, you would tend to think so, but in fact, you should consider rain and all other ambient conditions to have an impact on this. Everything from UV exposure to rain droplet size, and of course, the amount of rain is just changing from every part of the world to the other.
Let me ask about raindrop temperature, because I've heard some discussion about that. Like in colder climates, the raindrops are colder versus maybe, in Brazil in the rainforest where it may be particularly warm. Does the temperature have anything to do with rain erosion?
Yeah, we're basically seeing that almost every parameter have an influence on this. Everything from rain droplet temperature to ambient air temperature. Of course, speed, amount of rain, everything like that. And that's also one of the key points from the sale to DTU is that they're asking for more temperature control on this machine. So that's also going to be the first machine where we can actively cool the ambient air. And what they're basically trying to do is trying to divide all of these influences on the erosion process, which effects are coming from the temperature in the air and the temperature in the rain droplet.
Okay, that's very fascinating.
There's a lot of things going on, and that has been one of the big challenges in making this machine is that every small parameter is influencing this. We've seen the water quality coming out of the water tap having an impact, even though we have a water treatment system in this machine. We're just seeing it making a difference to the erosion process. And we have spent tens of thousands of engineering hours trying to get this repeatability up from machine to machine. And we're at a really good stage right now where we have a high repeatability, both in the same machine, but also from machine to machine.
Is there differences between saltwater and freshwater in terms of rain erosion impact, offshore, onshore?
I would have to guess so. We have never dared to put salt water in our machine.
I don't blame you. Yeah, it makes a mess. But that's fascinating. So pretty much every variable that everyone commonly thinks of, raindrop size, temperature, air temperature, UV, I think is interesting too. I think it is part of the solution. Impact how you build these test systems. So if you haven't seen R&D test systems, you got to go to their website because it's remarkable the work everybody does there. So if you look at the system, there's a lot of variables there. I think this makes sense to me that because we don't know as much as what we probably should know at this point, we have to not build test equipment that's very narrow in focus and eliminates a lot of parameters. We need to have sort of a wider variability, many more control knobs on the piece of test equipment. That increases the level of complexity for you, doesn't it?
It really does. And on the DTU machine, going back to that, we are seeing them basically speccing a machine which they can develop further in the coming years or the coming decade. We have a huge test chamber for them. So they want to build a high rain erosion test instead. There's a lot of things going on, and it has been a real challenge to get this repeatability up and trying to pin down all of these different variables impacting the results.
R&D test systems is full of test engineers. I think one of the hardest things about being a test engineer is you have to kind of solve the science before you build a piece of test equipment. So you have to have a really fundamental understanding of what is happening out there before you can go ahead and then start sketching out how this system is going to work. How many hours did you guys spend just learning about rain erosion and trying to grasp like what should be done?
Yeah, so the funny thing is that we're really in R&D test systems, we're machine builders and we're not rain erosion experts. And we get specification basically from our customers. And we're a project-driven company and we can just see the results and we can have a target of narrowing down these results, increasing the repeatability, and then focusing our energy on that. And what is actually happening then on a miniature level on the surface of the blade is really less of a concern to us. That is the concern of our customers who are operating the machine and looking at results.
You're manufacturing these rain erosion test rigs, we'll call them, and you have several out in the field. And this one at DTU sounds like it's like next level of a rain erosion test capability. What's next for R&D test systems in the rain erosion category? You're going to build this new concept, but if I'm an operator, just say I'm a large operator in Europe or the United States, shouldn't I? It seems like I should have one of these test rigs? Because I want to understand what's happening. I want to evaluate what's going on a little bit. It seems like there's not enough of these in the world yet.
No, I believe that's the case, and we're seeing these machines everywhere in the supply chain, from the OEMs to the blade manufacturers to the coating companies and test institutes, then backing up the entire supply chain. And there's room for more, definitely, because there needs a lot of testing, and we're also seeing companies using these just for increasing quality and production, sampling, testing different samples, etc. So you can never test too much. And also the fact that if you are able to, as an OEM or coating manufacturer, have your own machine, you are able to turn this knob down with the velocity, test for longer durations. That's not really feasible when you're going for a test institute. So having your own machine really opens that window. In terms of new developments, there's been like, in the last 10, 15 years, a long time, there's been discussions, should we do like sand erosion, hail erosion, stuff like that? And the answer must remain maybe, until somebody dares to change the machine. And that's also really the key thing, that now we have this machine and we have a high repeatability, and we can assemble results from one machine to the other. And nobody really dares to change anything drastically on this design now, because this is the window to all existing test results and data.
In the United States, we only have a couple rain erosion test facilities. Like I was saying earlier, they're just not uniform. It seems like we could use a dozen of your systems in the United States alone to help solve some of these problems, because we're inundated with different coatings, new technologies, new approaches from universities, from companies all around the world. There's just no way to evaluate them. And I think you're right. If you're a manufacturer of some of these coatings or systems, you have to have one of these rain erosion test rigs at your site to do long duration testing. That's the key. A lot of operators are starting to wise up and realize an hour or two long test probably isn't enough. You actually need to see something that's longer duration. And your system does it brilliantly from what I can see. So this is amazing. Niels, I think there's so much to talk about in terms of leading edge erosion. I'm really glad to have you on the program. And I know I'm going to get inundated with all kinds of questions, but I'm going to send them your way. So how do people reach you, and how do people reach R&D Test Systems?
So the easiest way is to go to our website, rnd-as.com, find contact information there. They can reach me directly as well, npe@rdas.dk.
All right. Well, great. Yeah. If you have rain erosion questions or interested in purchasing a rain erosion test rig, reach out to Niels, because the system they're producing is magnificent. So Niels, thanks so much for being on the podcast. Love to have you back.
Great. Thank you, Alan. Love to be back.